Yeah, so I'm going to tell you today a bit about quantum simulation of lattice gauge theories, and I'm going to make it some sort of an overview talk, since it's a relatively young field, as I will tell you, but this relatively young is already 10 years now, and it includes a lot of works and also some experiments and many, many details. So I will try to be as brief as general as I can and discuss the big picture. And I will focus less on the details, but of course you're welcome to ask me anything. And this is roughly based on some review paper that I wrote recently and was in this special issue of Philosophical Transactions of the Royal Society A, if anyone is interested in some more context. So, of course, in front of this audience, I shouldn't say much or say anything at all about lattice gauge theories. But we know that conventionally in these theories, what people do is to discretize both space and time, and the computations are done mostly using Monte Carlo in a Euclidean lattice, in a Euclidean space-time that we get after a V-quotation. And as we know very well, this has been very, very successful for so many things, such as the hadronic spectrum, but it has some problems. One is the inability to describe real-time evolution directly because we work with imaginary time and we lose unitary time evolution. And another thing, obviously, is the sign problem, which is super hard and stands in a way of understanding many important physical scenarios where we have fermions with finite density. So recently, again, in the last 10 years or so already, there have been new methods, new approaches, new proposals from the field of quantum information and quantum computation, which suggest to deal with these problems. One is tensor network states, which is something that I'm not going to touch today, although it's very interesting too, and I'm working on that too. The other thing is quantum simulation, and this is what I'm going to tell you about and define. Okay, so what's quantum simulation? The idea of quantum simulation, which was originally proposed by Feynman 40 years ago, is that we can take some physical model, some quantum model, which is either theoretically unsolvable, for example, non-perturbative, or numerically problematic, like the low energy limit of QCD. Something which is experimentally inaccessible. Again, if we think about QCD, I'd like to pull out a quark from a bound state, but which experiment will allow me to do this directly? So I have a model which doesn't allow me which I can't study using all these, let's call, conventional methods. But what we can do, since it's quantum, I can map it to another quantum system, which is fully controllable. That means that someone can build it in their lab and control all the parameters and control the dynamics and perform measurements and basically whatever we want. And this is what we call a quantum simulator. So in a sense, it's like building an analog quantum computer, some quantum device which is not universal, can't solve any problem, but is identical or approximately identical to another quantum model which we would like to study. So then if we manage to design and build such a quantum simulator, we can simply study experimentally things that we couldn't have studied otherwise. And this is the idea behind quantum simulation. Now, if we want to talk about quantum simulation of lattice gauge theories, why would that be interesting for us? Let's just have a look at these two problems that I mentioned with Monte Carlo. One is the problem of real-time evolution. This is an artifact of going to the Euclidean space. But here we have no problem. When you build a quantum simulator, you actually build some quantum system. You can prepare a state, tune the dynamics on, let it evolve in time, see what happens. It actually evolves in real time. So this is not a problem that we have. Another thing is the sign problem. Again, this is some artifact of the way that we choose to compute when we do Monte Carlo, when we do Euclidean path integrals. If we manage to map our model to some simulator, to some experimental system, which includes fermionic degrees of freedom, then fermions are fermions, not represented by any Grassmann fields. we don't need to compute any determinant. We can just let it evolve in time, do whatever we want to do with the experiment, and at the end, measure whatever we want to measure. So this could be a way to go around this problem too. And indeed, this field it is something that which started roughly 10 years ago, as I already said too many times. But today it's already very, very big, which is a good sign. If this is something which at the beginning interested only some quantum information theory groups, and this is where I came from back then, and we were thinking about ways to map gauge theories to atomic systems and to solid state systems, and cared less about the feasibility and more about the theory, just devised some mathematical mappings from one world to the other. And this is what I call here the step 1 review papers. These were some early proof of principles. But today, the nice thing is that over the years, 2 great things have happened to this field. One is that it has become experimental. There are quite a few experiments done in this field which actually implemented some quantum simulators of lattice gauge theories. These are mostly one-dimensional, one space dimensional, I mean, or very small size or abelian theories, but the things get more and more scalable and starting to approach more and more the proposals from the beginning that were already aimed at non-abelian theories in higher dimensions and so on. And nowadays you can look at more contemporary review or roadmap papers where people which are both theorists and experimentalists already join forces together to meet each other and think of actually building some simulators, some quantum devices that will be able to study non-trivial models and teach us some new physics. So unlike the conventional setting in lattice gauge theory, here we work in the Hamiltonian picture because we actually build states and let them evolve in time. This means that the lattice in our case is only in the space dimensions. Time is a continuous coordinate and it's real. But just like in the space-time formulation, the matter, which is mostly fermionic, resides on the sides of our lattice, and the gauge fields occupy the links. And this is the first challenge that we meet when we want to map a lattice gauge theory to some atomic, optical, or solid state device. We need some simulating platform that will be able to describe both fermionic and non-fermionic physics. This is the first thing that we need. And many simulation devices, many quantum computing devices don't allow us to do it. Let's move on and see which other challenges we have. So of course, in the core of the gauge theories, we have gauge transformations. Doesn't matter if we are in the continuum or on the lattice. These are transformations, as we know, which act on both the matter and the gauge degrees of freedom. It's local, so any gauge transformation which is parameterized by an element of the gauge group transforms the matter, a single matter site, and all the links of the gauge fields around it. And in a gauge invariant state will be invariant under all these transformations separately. If we have a compact Lie gauge group, we will have Gauss laws from the gauge generators. But when we want to build a quantum simulator, when we want to take some quantum device in somebody's lab, this forms another challenge for us because these systems in general don't see such local symmetries. For example, if I take an atomic system, it will have some global symmetries such as conservation of total atomic numbers, things like that. But how can I impose some local symmetry, some gauge invariance? How can I make the system be gauge invariant? How can I make sure that this symmetry is not lost due to some decoherence during the simulation? Or maybe there is a way I can go around it and simulate something which doesn't have this local symmetry strictly. This is another challenge that we have when we want to design such a simulator. And this gauge invariance also
question.
Yeah.
Are you thinking of the digital quantum computers a la Google, or are you thinking really about atomic physics platforms?
Both. It can be done in both ways, and at the moment it's at the moment this part of this presentation It's related to both. Obviously, when you do something digital, a la Google, as you said, you can just write some sequence of quantum gates that will make sure that these things that these symmetries are satisfied, and it might be less difficult. But on the other hand, you will have to deal with things like error correction, etc. When you do it with atomic systems in an analog way, there are other ways to do it. I will discuss them briefly, which allow you, for example, to map symmetries of the simulating platform to this symmetry that you want to simulate, and so on. So, but in some way, you need to deal with this in both kinds of quantum simulation.
Okay, thank you.
Thank you. So this challenge has another side effect, because here I demonstrated for an abelian case of U1 of compact QED, but in any case, if we have many, if we have a local symmetry, it means that we have many local constraints, one per lattice sites, and this splits the Hilbert space of our theory to different super selection sectors having to do with what we call static charges that are disconnected by the dynamics. So obviously, if we might be interested in more than one sector, but if we don't, it means that simulating the full Hilbert space is quite a waste. So maybe there is a way to save computational resources by actually implementing a single sector or something like that if we need. This is another challenge. Then what are the interactions that are allowed in such theories that we see in Hamiltonian, such as the Kogut-Susskind Hamiltonian? These are some local interactions that have to preserve the symmetry. They commute with the Gauss laws, with the generators of the symmetry transformations. So one option, the matter gauge interaction, the lattice version of minimal coupling, is when we have a matter particle which hops from one site to the nearest neighboring site with this psi dagger psi, for example, in this fermionic case. And then you act with some gauge field operator, a very particular one that makes it gauge invariant, which we can see as a connector, and such that gauge invariance is maintained. So this is one kind of interaction that we must be able to implement. And another one, which is quite challenging, is the plaquette interaction, which in the continuum goes to the magnetic term. Here it's a self-interaction of the gauge field. The gauge field interacts with itself, and it involves 4 links around the unit square around the plaquette. That's a highly nonlinear interaction. We don't get it for free in these possible simulation platforms. And if the group becomes more complicated, non-abelian, we have so many terms here, and it becomes a mess. It's possible to do it, but it's not a trivial task. So this is what I'd call the third challenge, this complicated 4-body plaquette interactions that we must be able to implement somehow. And now I want to tell you a bit about how we can actually deal with these challenges. So first of all, naively. What do I mean by naively? It's not naive at all, but it means that we don't try to go around the constraints. We just try to deal with them directly. So, for example, one challenge that we mentioned is that we needed both fermionic and non-fermionic or bosonic degrees of freedom. This can be solved, as has been proposed and experimentally implemented by several people, using cold atoms in optical lattices. These are systems in which we trap very, very cold atoms in lattices which are created by laser, by optical potentials. And of course, we can play with the atoms. One can use different atomic species that will be either fermionic or bosonic. And when you tune your lasers wisely, you can also make sure that some atoms, the different atoms, see different lattice potentials. And this allows to trap fermions on the sites for the matter, bosons on the links for the gauge fields. And the next thing, which is of course non-trivial, is to play with their interactions and make sure that we get what we need. But this is a starting point. If we want fermions and bosons, the system that will allow you to do it within the available quantum computing platforms is cold atoms. And with these cold atoms, going back to the earlier proposals, there are different ways to impose the gauge invariance. The first one is to impose it effectively. It's not exact, it's not very robust, but that's the first method that was proposed. And in this, what we do is that we can somehow design with the atomic ingredients some Hamiltonian, which is not the full thing, which is not gauge invariant. And we add to it a constraint, which is the generators of the symmetry, or the generators of the symmetry squared. And if this constraint is very strong, we can split the spectrum of the theory to different sectors corresponding to different eigenvalues of the constraints, and each of them is gauge invariant. So then if you tune all the parameters right, and it's not trivial, but there are ways to do it, you can see with all these proposals from the past, we can, using perturbation theory, we can build an effectively gauge invariant quantum simulator in one of the sectors. So this was proposed many years ago, and it's a bit more complicated method because it involves and requires a lot of fine tuning. And of course, if the symmetry becomes non-abelian, you add more symmetry generators. It becomes you need to add much more terms as constraints to your Hamiltonian. But recently, this was revisited and simplified a bit. I told you that the constraints had to be quadratic, but with dissipation and with other methods, it was shown that they can be linear. And also with a control theory trick called dynamical decoupling, you can make it linear and simplify. But these are the technical details. The more interesting thing to talk about, I believe, in such an overview talk, is the second analog approach, in which you take symmetries that you already have in your quantum simulator and you map them to the symmetry that you want to simulate. What do I mean? If we build it out of ultra-cold atoms, we just need to look which interactions we have available with these atoms and what is conserved locally with such interactions. And the answer is the atoms are so cold, ultra-cold, that effectively the only relevant interaction that they have is a collision interaction, which is approximated by a delta potential. And in such a collision, what is conserved is the hyperfine angular momentum of the atoms, and the collision is very local, since it's just collision. And then we can use it to simulate the local interaction that we want in the gauge theory, and we need to somehow map the hyperfine atomic levels to different levels of the gauge fields and the matter particles. We just choose the hyperfine levels of all the participating atoms such that the processes allowed by conservation of angular momentum, which is a local interaction, will be exactly those allowed by charge conservation or Gauss laws, which is also some local symmetry. So that's one way of doing that. In what we call an analog simulator, we truly take a Hamiltonian with some interactions and we map it to the Hamiltonian that we want with the same interactions, with the same symmetries, just by properly choosing the atomic levels. And this was actually implemented well. A first building block of that was implemented not so long ago in Heidelberg, and this is a very exciting result. However, when we want to create the plaquettes, it's more challenging. Yes, there are ways to create plaquettes in methods similar to what I just discussed, but usually they will involve some high orders of perturbation theory and some effective expansions, which make it a bit less robust. And also we can get only very weak interaction terms. Another way to do it is to combine some digital ingredients, some sequences of quantum gates. So I was asked earlier about whether the simulations are digital or analog. What I showed you so far was analog. And what I'm going to show you now can be thought of as both digital, just sequences of quantum gates, or a combination between the two in some hybrid or analog digital way. You can do some of the interactions in one way, some in the other way, and have something in the middle. And the story here is to use some control atoms. Suppose I'm going to show you the simplest example when the gauge group is Z2. And I just have a two-level system on each link. And the plaquette interaction looks like this, a product of 4 sigma X operators on all the links. What I can do is to use another degree of freedom, a control, let's call it an atom, but it can be something else, or a control qubit if you want. And I can act with a sequence of two-body interactions of the very common ones in quantum computing, entangling the control sequentially with each of the physical qubits on the links around it, such that if I act with the sigma x operator on the control, it will be physically equivalent to acting with the product of the four sigma x operators on the physical qubits. So with a sequence of two-body operations and a simple operation on the control, I can exactly generate a complicated four-body interaction. So this was too difficult to do with the purely analog methods. Like this, I can just add some digital tools and achieve something like that as well. And this can be generalized to any gauge group that we want. In some cases, it's more feasible than in others, obviously, and it's still something which is being studied. But this has really been applied and used in the last few years in some proposals for actual quantum simulations. This looks like one of the most promising methods for plaquette interactions. And recently, we used this method with my group and collaborators in Madrid to propose the first quantum simulation of a lattice gauge theory with a nanophotonic device. And the advantage of this thing, I will not get into all the optical details. The advantage of these things is that instead of sequentially making the control interact with all the four atoms, it can interact with all four in parallel, because this is some system which has long-range interactions. So instead of mapping a sequence of two-body interactions to a four-body interaction, we can just map two-body interactions that are done in parallel. We can map them to a four-body interaction, which saves us a lot of expensive coherence time, because the systems heat up and stop being quantum in a sense pretty fast. Now, the other way, I said that these were the naive ways of dealing with all these challenges directly, but maybe we can get rid of them. Maybe we can go around them. And this is what I want to show you in a few minutes. Basically, I mentioned three main challenges here: that we need fermions as well as non-fermionic objects, that we need to deal with the gauge, with the local constraints, and that we need to implement the plaquette interactions. And I'm going to tell you briefly about two kinds of methods that have been proposed recently, and each allows to consider, to get rid of two of the three. And I will also mention another approach of loop string hadrons, where you simulate things that are already gauge invariant, and there was another talk about it in this workshop. I'm going to focus on other methods. One in which we can eliminate the matter, which makes use of the fermions, which takes care of the fermions challenge and the gauge constraints. And the other one going to dual formulations. This has to do with the gauge constraints, and it makes the plaquette interactions easier. So let's see. What do I mean by eliminating the fermions? So fermions, if I don't have supersymmetry or something like that, they are subject to a global Z2 symmetry, the one having to do with parity superselection. I don't consider superpositions of even and odd number of fermions to be physical. But if this symmetry is local, and this can happen naturally if my gauge group contains Z2 as a normal subgroup, I can use my global Z2 constraints for somehow locally transferring the information on the statistics from the matter to the gauge fields. There is some procedure that allows us to do it using the Z2 subgroup of the constraints, of the local constraints of the Gauss laws. And this allows us to break fermionic creation operators in this way by these two operators which are constrained, a Majorana fermion which accounts for the statistics, and some hardcore boson which accounts for the physics, in the sense that this is what will appear in fermionic bilinears, in charges, and so on. So we have come up with a local unitary transformation, some controlled operation, which using the Z2 ingredient of the local symmetry, it allows us to replace locally all the fermionic creation operators by some hardcore bosonic operators or spin operators, if you want. And the price that we have to pay, instead of normally one uses the Jordan-Wigner transformation, which gives rise to crazy non-locality if we're in more than 1D. Here, what we get is some corrections which involve the gauge field. So each interaction of matter and gauge field now gets some, is now multiplied by this factor that we have here, which depends on the sign of the electric fields. This is a U1 example, but it can be done for other gauge groups too, on some neighboring links. Okay, so it becomes slightly non-local. The range of interactions is enlarged a bit only to neighboring links, but it's not something that includes a string or something which is very non-local, such as what you get with Jordan-Wigner. And this really opens the way. Thank you.
5 minutes.
Thank you. And this really opens the way for quantum simulation of lattice gauge theories with fermionic matter in more than one space dimension, using platforms that don't offer fermionic degrees of freedom. You use the result of this mapping. This mapping allows us to rewrite lattice gauge theories with fermionic matter as lattice gauge theories without fermionic matter with local interactions. And in some cases of UN gauge groups, the matter can be removed completely. We can be left only with gauge fields, with broken gauge invariants, only the link variables that interact with one another. Much smaller Hilbert space, no local constraints. It's a very simplified system to simulate. And I don't have time to talk about all the details, but the way we eliminate the matter here is very, very similar to the procedure which is done in the unitary gauge fixing that is used when the Higgs mechanism is studied. And recently we wrote we proposed it for arbitrary gauge groups. Recently we showed how this can be done explicitly for the most simple case as a proof of principle for a Z2 quantum simulator. And we actually wrote down, and this is a more digital approach, a sequence of quantum gates that allows one to simulate a Z2 gauge field coupled to physical fermions without actually having the fermionic Hilbert, the fermionic Fock space and the local constraints in the simulating system. The other thing we can do using dualities is to solve the gauge constraints. So in QED, in two space dimensions, we know that we can get some dual formalism with Plaquette variables, with magnetic fields, and no local constraints. And in 3+1, we also need some local constraints for it, but one can go to the dual picture. And this might be useful for quantum simulation going to the dual picture, because, for example, the four-body interaction of the plaquette becomes a non-interacting one. And the methods to do it for pure gauge theories were discussed in the 70s and also recently in a way that applies more to these quantum simulators, but also in a work by ours and another work by other people that was done in parallel. We proposed two different ways actually to do something similar when matter is present, with to write down a different dual formulation of a billion lattice gauge theories, which doesn't have plaquette interactions, which doesn't have local constraints, hence solving two challenges with matter. And this is something with, and all this idea of dualities opens the road to quantum simulators of more general theories, because actually this inspired us to think about taking a duality transformation, which normally is just some brilliant, but just a mathematical trick, and implement it physically on a quantum system, implement using a sequence of unitary operations and measurements, convert the quantum states of a system in one formulation to its dual formulation. And this we thought about it using some hints that we saw when studying the simulations of lattice gauge theories. And this actually allows to simulate both sides of a duality transformation, which we're looking at now, but this might turn out to be a powerful tool for quantum simulation, because when you simulate sometimes a model with that admits a duality transformation, in different regimes, different formulations are better, and having both in the same simulator and being able to connect them physically in the lab can be a great benefit for the quantum simulation. So to conclude, the quantum simulation of lattice gauge theories is subject to several challenges, as I mentioned: fermions and non-fermion and bosons, gauge invariances to be maintained, imposed, or overcome, and we have the complicated plaquette interactions. I showed you some way to deal with it directly and indirectly. And yeah, the field of quantum simulation of lattice gauge theories is really exponentially growing, and there's a lot of experimental study now, but also there's plenty of room for theory that still needs to be done on the road to making it non-abelian, 3+1 dimensional, and so on. So it's really, in my opinion, a beautiful field. And yeah, with that I conclude. Thank you very much.
Okay, thank you. Any questions? Richard?
Yeah, it's interesting, this control thing you mentioned.
Yeah,
the C thing.
Yeah.
Yeah. How is the control done? I mean, is a wire brought in to pull it on and off? I mean, what's the external control that gets it to go around?
So it really depends on the simulating platform. When we first thought about the first way we suggested to implement it involved some atoms that are trapped in laser potentials. Okay, so you can think about all these red, blue, green circles as some minima of laser potentials, and some atoms are fixed to this point. And then you can slowly, adiabatically move the potential of this control and just, sort of classically move it to meet each of the other atoms, and then they scatter off each other. There's some two-body collision, and it gives you that.
I guess it's maybe hard to say, but you have this thing ticking around apparently in some clock, right? So what is the device actually doing when that ticks around? I mean, if it's purely analog, you let it go and it just evolves, right?
Yes.
So now
yes.
you're
this is purely
imposing some other thing which you call digital. So what does that mean? Is there
so by digital I mean so this is sort of this plaquette thing, you can think about it as digital in the sense that you build it out of a sequence of these gates, of these unitaries. But each of these gates you build in a purely analog way. This is why perhaps it should be called analog digital. But this is when you do it in the way that I told you right now. But if you think about another thing that I told you, in this system, for example, what you have is that naturally you have some long range interaction of each of these controls. So the controls are the green circles here. Each of these controls is coupled through some, the whole thing is in some cavity, and through the cavity mode, some electromagnetic field, which is inside here. Each of these control atoms sees all the physical, the blue atoms around it. And if you properly tune the laser and some external magnetic fields, you can make sure, first of all, that you only meet the nearest neighbors, and then you can speak with all of them in parallel, and then you can switch it on and off almost suddenly, okay, with very short pulses. And this could be seen as something more digital in a way. But
so there's a classical computer outside which is pulsing some laser or something as the analog system evolves. Is that right?
Right.
Okay.
Yes.
Yeah, that's what I wanted to know. Thanks.
Yes.
But you didn't mention the preparation of the initial state. That's one of the things that's also very hard. So do you have any comments on that?
So of course, this heavily depends on the simulating platform. But normally, when you build such a quantum simulator, if you think about atoms, for example, one particular thing to do would be to prepare the system in an initial state in which is some limit of the theory, some non-interacting limit when the interactions are switched off. And then it's easy to prepare it because you can just, for example, if you have an atomic system, you can directly control how many atoms you put on each minimum, on each potential well. And then you know for sure that you created this. Then there are ways to get to more interesting states. So it depends on the physical scenario. You can start switching the interactions on adiabatically and adiabatically grow the ground state. You can quench it and perform some measurements and see what happens. There are different ways to do it. But if you manage to create some ground state, which is gauge invariant, and this you do by considering one of the extreme cases that you know what they are, and you implement some dynamics, which is gauge invariant, you know that the symmetry will not be broken.
Yes, thank you.
Thank you.
Any other questions? Okay, let's thank the speaker again.
Thank you very much.